In this section, we're going to consider an example of the extended Kalman filter along with code to implement the example because we want to try something simple first. It's just a generic example, and then in later section we will look at how to implement this for estimating cell battery state. Here we are going to define a fairly simple nonlinear system. The new state equals the square root of 5 plus the old state plus some process noise, and the output is computed to be the state cubed plus some sensor noise. And for this example, we'll set the process noise covariance to 1 and the sensor noise covariance to 2. We have a scalar state, which makes it a little bit easier to be able to think about and to operate with, and a fairly simple description thereof. In order to implement the extended Kalman filter, we need to be able to determine the A hat, B hat, C hat, D hat matrices of the problem, and that's something done algebraically, analytically, not numerically. We have to do this before we implement the filter. Going back to the definitions, A hat is the total derivative of f with respect to x, which we already identified was the same in this case as the partial derivative of f with respect to x, evaluated at x equals x hat. What we do is we say, okay, what is f? There's f. Well, f is this. Root 5 plus x added to w, so it's the partial of root 5 plus x added to w with respect to x. We know that the partial derivative of w with respect to x is 0, and then the partial derivative of the square root of 5 plus x with respect to x, we can write this, I like to think of it this way, as 5 plus xk to the 1/2. So I end up with 1/2 times 5 plus xk to the minus 1/2 in our answer. So this is what we have here, but we would have an x, which we have to replace with x hat, which we get in this result. Moving on to b hat. B hat is the partial of f with respect to w. So once again, I have f. I put in f there, and the partial of root 5 plus x with respect to w is 0. Partial of w with respect to w is 1, and that is my final answer. There's no w's in the answer, so I don't have to replace anything by w bar, but if there had been a w, I would have put a w bar in its place. The next thing is c hat, and c hat is the partial of h with respect to x, and h is this. We substitute in x cubed plus v, and taking the partial of x cubed with respect to x, we get 3x squared, and partial of v with respect to x, we get 0. And so the 3x squared, we substitute the x with x hat k minus, and our final answer is going to be 3x hat k minus squared. The last is d hat, which again takes the partial of h with respect to something, to v, and h is again x cubed plus v, and taking the partial of that with respect to v gives me 1. That is the hard part of implementing an EKF. For this example, it wasn't terrible, but for some applications it can be fairly tricky to come up with these derivatives, especially if we have a system with a vector state rather than a scalar state. In that case, we have to use vector derivatives instead of scalar derivatives. In any case, we've done that here, and we're ready. We have all the information that we need to be able to implement the extended Kalman filter steps from the previous section. And there is a note that in this code, the steps for calculating the A hat, B hat, C hat, D hat matrices depend on the nonlinear system. We just derived for this system what those matrices would be, but of course for any other system there would be different matrices that would have to be implemented. If you have it handy, you might put this code side by side with the linear Kalman filter code, and you'll see that there are some similarities, in fact a lot of similarities in the code, and it might be instructive to see where they're the same and where they are different. We start out by defining sigma w and sigma v to be the given values for this problem, and I define a variable max iter which says how many simulation iterations or time steps I want to simulate, and that is something that's up to you. I need to have, again, as in the last simulation, I have some inputs to a real system and some outputs from the real system, and over here we're going to have an EKF operating in parallel. I need to, in my simulator, be able to implement the EKF, but I also need to be able to emulate the simulation of the system. And we would not do that in a real EKF application. Instead, we would simply measure the input and output signals, but here we need to do both. So for the true system, I'm making an initial state, and in this case I'm choosing it somewhat randomly. I'm saying that it's 2 plus rand 1. The initial estimate of the state, x hat, for my filter, I'm saying is 2. Now that's the expected value of this, but they are different. So our filter will not be initialized with perfect knowledge, and we will represent that by saying sigma x equals 1. So here I've got 1 times, where that 1 is 1 standard deviation times rand 1, and this here is 1 squared to get the variance from the standard deviation. The prior input we don't know, we'll say it's 0 for now. The next steps, we reserve storage for the true state and the estimated state and the covariance of the estimated state, as we did before, so there should be no change to those lines. We enter the main simulation loop, and while I've talked about the filter as having steps 1A, B, C, etc., here I'm implementing what I call in this code step 0, which is where I'm computing the A hat and B hat matrices to be used later on. And A hat depends on the prior estimate, not the present prediction, so I have to compute A hat before I update X hat with the present prediction. That's why it's in step 0. So A hat is 0.5 over square root 5 plus X hat. That should correspond with what we saw before. And B hat is equal to 1. Now we do EKF step 1A, where I propagate the estimate from the previous time sample through the state equation to get my prediction of what I think the state is right now. So this is X hat K minus, this is X hat K minus 1 plus, propagated through the equation to give me my prediction. Step 1b, I simply implement the equation that's given. It's sigma x equals A sigma x A transpose plus B sigma W B transpose using the hat matrices, and where this here is sigma tilde x K minus 1 plus, and this is sigma tilde x K minus. And so at this point, we simulate the operation of the actual system in the background. The actual system in this case has no deterministic input u, so I don't need to actually find that, but there are the random inputs w and v. I create those in the same fashion that we did with the linear Kalman filter code. And then we compute the true output, which is the true state cubed plus sensor noise, and we compute the true state for the next time around. So this here is xk, this is xk plus 1, which is what we will use then. It's time to go into step 1c, and again I need to compute the C hat and D hat matrices before I stomp on anything. So that's gonna happen here. So C hat is 3x hat squared and D hat is 1, and y hat equals x hat cubed. The Kalman gain matrix we compute given the sigma y given the equation in the previous section, and we compute the Kalman gain just as listed there. There's no surprises. And then step 2b, we make x hat, this is x hat plus, this is x hat minus, added to L times y true minus y hat. And then we do something that's a little bit different from anything we've seen yet. This is not in the math anywhere. This is an ad hoc step added to increase the robustness of our filter. No one taught us that we had to do this, but if you run the code without this a few times, you'll find eventually it's going to crash unless we do this. So what's going on? Well, if you go back to the equation of the state equation says xk plus 1 equals square root 5 plus xk, all added to wk. In the real system, the state is never going to be smaller than minus 5. If the state somehow became smaller than minus 5, that square root would give us a complex number, and my real valued system would all of a sudden become a complex system, and that's not what we had in mind. So, if my estimator is a little bit confused at the beginning, because maybe the estimation error bounds are large and they haven't converged yet, it's possible that I would get an estimate out of step 2b that is actually less than minus 5. Here I am putting limits on what I will consider an acceptable estimate by saying anything below minus 5 is unacceptable. So I'm going to compare the estimate that I achieve to minus 5, and I'll take the bigger of the two. And doing that makes sure that when I get to this step 1a next time around, I don't get complex numbers in it. This is the kind of thing you always have to be on watch for inside your Kalman filters, is how do I take the theory and realize what the theory is kind of sort of shoving under the carpet and forgetting, and modify the code in order to give me something that's more robust in practice. A battery management system is going to be running with no supervision itself. There's no engineer sitting in the back seat of your car and looking at the outputs all the time to make sure everything is okay. So the code has to be able to handle even very infrequent strange cases. Step 2c, no surprises. This is exactly what we were told to implement. Except in this code, I'm doing something new that I didn't do last time around, is I'm adding some of the robustness code that we saw in a previous section, where we want to ensure that our covariance is symmetric and positive semi-definite. So I take the singular value decomposition of sigma x, and I compute this intermediate h variable, and I replace sigma x by this computation, which is guaranteed to keep everything to be positive semi-definite and symmetric. Then after that, I store things and I plot things in much the same way that we did last time. Here are the results that this code gives for one example simulation. The inputs are random, so if you copy this code and paste it and run it yourself a number of times, you'll see that sometimes the code appears to do better and sometimes it appears to do worse. This is a relatively typical example of the extended Kalman filter in action for this particular set of equations and assumptions. In the left figure, the black solid line is the truth, and the green solid line is the extended Kalman filter estimate, and the dashed lines are the error bounds produced by the EKF on the estimate. And I think you could argue pretty convincingly that most of the time the EKF estimate is quite good. There are a few cases like there it's not so good, and there it's not so good, and maybe there it's not so good, but Other than that, it's a reasonably decent estimate of the true state. They're tracking each other. They're going the same kind of direction, maybe not quite as far every time, but the same directions and all of that. The picture on the right tells a story a little bit more clearly, though, that is a little bit concerning. So here we plot the estimation error bounds, which is truth minus estimate. And again, if you look only at the error, you could say that the EKF is doing okay. The error is within certainly plus minus 0.5 most of the time, and even smaller than that if you don't want symmetric limits. So say between 0.1 and minus 0.5 most of the time, which could be quite good for this application. I don't know. But what concerns me is when I look at the error bounds, the error should always be inside of those bounds, and it very rarely is. So in the linear common filter, we found out that 99.7% of the time the error was inside those bounds, which means that the bounds are quite reliable to be used as kind of worst case in some application of the state estimate to driving a vehicle. Here, I'd say probably close to half the time the error is outside of the bounds, meaning that the bounds are not very useful for telling you how accurate and inaccurate your state estimate is on a dynamic basis. So that's a bit of a concern here, and we'll keep that in mind. We're not quite ready to move on to a sigma point Kalman filter yet, but when we do, we're going to take this result here, and we're going to run a sigma point Kalman filter on exactly the same data, and we're going to compare the two different filters for how well they can compute an estimate and how well they can compute error bounds. And you'll see that we do get an improvement. So that's our first application of an EKF, and it's not very battery related. But now that you've seen the equations we need to implement, you've seen one example of implementing the equations, we're ready to move on and look at how we would implement an EKF using the enhanced self-correcting cell model. And the first thing we have to do up front is find A hat, B hat, C hat, D hat matrices, and then we're ready to do our implementation and see how well it works.